In this video, we're going to discuss differentials. So let's just jump right into a definition. Differential dx is an independent variable. The differential dy is defined dy equals f prime x dx. Now, that's really not terribly helpful. We still really don't understand what's going on here, so let's really spend some time diving into these and understanding what these differentials are talking about. Now, we've seen dy and dx before. We've defined a derivative as this dy over dx, and that is a Leibnitz notation, the dy over dx. And it kind of looks like I've just rearranged this, right? We've just kind of rearranged this notation and said that dy equals f prime dx, and that's completely false. That is not what we are talking about at all with our differentials. This Leibniz notation, this comes as a unit, right? This is saying that the change in y over the change in x. It's not saying dy over dx. We don't read it like that. If anything, we say dy dx because it is saying the change in y with respect to the change in x. It is all one piece. It is that resultant derivative that we get. The dx, dy we were talking about here, the differentials are standalone components. We're not just breaking up this Leibniz notation. So let's think about what's going on. Let's view a function. Let's view the graph of a function. So I'm just going to do a curve here. And if I look at this function, we'll call it f of x. We could define some points around this. So for instance, maybe I'll define this as my point A. And that would mean that over here we have our f of A. And so one way we've defined motion, for instance, if I want to move over by this amount right here, well, we could redefine it as a point. We could say it's point B or what have you. Or we could also say we've moved by delta x, meaning an actual change in x. And that would mean this new point is a plus delta x. And we do this with the difference quotient. We just call it h rather than delta x. But that gets us to a new y value. Gets us to an f of a plus delta x. And we could calculate all these points, and that would, we could get all those values. It wouldn't be terribly hard, but one thing we did, what we did in the last lesson, we looked at this idea called linearization. So in linearization, what we do is we say, well, rather than dealing with this more complex function, and, it could be, anything could yield this curve. It could be some crazy portion of a sine graph, or it could be some, composition or combination of functions where we have sine x plus the cubed root of x minus the square root of 5x minus 2. We just don't know where this little portion of the curve is coming from. I haven't defined the actual function, so I might not want to deal with that actual crazy function. I might want to just say, well, let's look at the linearization. And we saw in the last video that as long as we're pretty close to that point of tangency, or the center of linearization, we have a pretty good model. And we see that, in fact, here at a plus x, we're not real far off of where the line actually is. And where these differentials come in, we are applying a derivative, right? We have a derivative sitting right in there. We're essentially looking at the linearization, and we're seeing what's going on with this linearization. So we still have the center of linearization, that point A. But if I'm looking at the blue, now this amount here, because we're looking at the linearization, this is our dx, representing the amount of change. We've seen how we've called this dy dx the rate of change of y with respect to x. We're looking at the amount of change now because it is just that singular variable. It's not a rate of change. It's not in that differential format. It's just an amount. How much have we slid over on the x? And then conversely, what we get back out of that is how much we have changed on the y. So let me draw another line in here. We were at this green line initially, and so we're looking at how much have we changed right here. So this distance right here would be the dy. As we move over by dx, how much have we changed on the dy? Now, we could have found a delta y before too, right? So if I, this is still my initial height, that's still the initial f of a, and then if we draw a line directly up, this black dotted line here, this would be our delta y. The delta is representing an exact amount of change. So the delta y there again being the whole way, go ahead and make that dark, being the whole way from the green line up. delta is always representing that actual amount versus the dy dx. The dy is an approximation based on that linearization. So the dy, again, this amount, and here this little green line. And so we can see that they're not exactly the same, and the goal with the linearization is to drive that very, very close to being the same. We would like it to be the same, or at least very close to. And so, if we'd picked a point a lot closer in, as we discussed with linearization, we're going to see almost no difference between the delta y and the dy. They're going to be pretty much the same value. As we get further and further away, that grows more and more, and so it becomes less of it's not as good of an approximation. It's a worse approximation as we move further from that center of linearization. Now this amount right here, that's the difference between the delta y and the dy, and that is the amount of error. And so we can always find the error of our linearization by taking the delta y and subtracting the dy. And usually when we're talking about error, we don't care about whether it's above or below. We could look at that too, but a lot of times we'll take the absolute value there to just say, hey, this is the amount of error. We don't necessarily care about the direction. So these differentials are getting into the fact that we're looking at motion. We're looking at an amount of change. So we're saying, hey, I can predict this point pretty well based on the linearization, a more simple function. But when I do that, there's also some error there associated with that. So let's take an example where we put this to work. All right, so we want to use the function f of x equals 2x squared plus 6x minus 3 to find the change delta f, so that's the actual amount of change, the estimate df, so that's the amount of change based on the linearization, and then we're going to figure out the approximation error, meaning how much was our estimate wrong by, how much were we off by. So that delta f, again, just to kind of go through the components, delta f is talking about that whole amount of the actual function. The dy is that smaller amount based on the linearization, and then the error would be how much they're off by. And hopefully if we have a pretty good model, we'll see that they're pretty much the same. So we're going to do this for a center of linearization at 1, and we're going to look at a dx of 0.1. So the first thing I need to find is the actual change in f, and so that means I need to figure out where I'm starting and where I'm ending. So I'm obviously starting at 1, that is my center of linearization. The dx, because it's positive, that means we're going forward by 0.1, meaning we're going to a final position of 1.1. So we're going to plug these numbers in and find out what we get. So we have 2 times 1 squared, that's going to be 2, plus 6 is 8, minus 3 is 5. And then we're going to do the same thing with 1.1. So this one I'm going to go ahead and type into the calculator just to make it a little bit easier and faster. So when we type all of that in, we should get 6.02. And so now we can calculate the actual change in the f, 6.02 minus 5, that is equal to 1.02. Now, that's our part A. That wasn't terrible, but that was a relatively simple function too, so we can imagine that as the function gets more complex, it's going to be easier to use this estimator. To remember, the df is talking about the f prime times the dx. So just to write that out again, df equals whatever the f prime is at our value times the dx. So first thing I'm going to need to do is find the derivative of the function. F prime of x would be equal to 4x plus 6. Very easy derivative to calculate. And so now the differential, df, we're going to take the center of linearization, or the 1, plug it in. 4 times 1 is 4, plus 10 is 4 plus 6 is 10. And then our dx is 0.1. And so multiplying those two things together, we get a value of 1. And so that would be our df. The actual change in the y was 1.02, but what our linearization predicted, what our differentials give us, the change of an amount of just 1. And so then for our part C, if we're looking at the error, we would have the 1.02 minus the 1. These are our absolute value bars on the ends because we don't care about the direction of the error, we just want the amount. We get an error of 0.02. So that's very, very small. If we really consider what that error would be as a percentage, we have 0.02 amount of error over an initial value of 1.02, which means the error is something around 2%. Very, very good amount, very low amount of error. Now, is that good enough? It depends on our scenario, right? And this is where tolerances come into play. And so, if we're looking at something where we're manufacturing tiny little, say, screws for an assembly process, maybe they need to be even more precise than that. If we're manufacturing maybe giant robotic arms that they're going to be many feet, 2% error might be within our realm there. So it really just depends on what our scenario is. So again, the df is representing that approximate amount of change based on linearization versus the delta f is the actual amount, and then whatever the difference between the two is our error. Now these differentials, we're going to see them in other places too. These are just representing the amounts of change. They are an amount of change just based on an approximation based on a derivative. So nothing too complex.